All right, let's finish up bending stress here today. All right, so if you got a beam and you apply a load to it, it bends a bit. And you get a neutral axis running down the length of the beam. It runs down through the centroid, basically, of the cross section. And you're going to, on one side of that neutral axis, you'll have tension, the other one compression. Neutral axis has neither. That's why it's called the neutral axis. All right, so if we look at these bending relationships here, what we find is there's a linear relationship, or a pretty close approximation, you might say, to a linear relationship between the distance from the neutral axis and the amount of strain, either tensile or compressive strain in the beam. So that's pretty much a linear relationship. The further you go, the more you have. So we start with the strain, but we can multiply through by E and get to the stress also. So basically we have this idea that as you get further from the neutral axis, which we call a distance y, the stress and strain vary in a linear sort of fashion. So there's a constant value there of sigma x over y. Okay. All right, now these stresses relate to the moment you get from the moment diagram or moment equations relates to the stresses that build up in the beam. You can take those stresses, one side of the neutral axis will have compression, the other one tension. You can then find the moment and relate it to those stresses. What you do is you find the force of each one of those little stresses acting on a differential area, dA, so that'd be sigma x dA would be the stress, or the force. Multiply that by y, which is the distance from the neutral axis, and that gets you a moment. If you add up all of those stresses times their areas, times the distance they are from the neutral axis, you get the total moment, and that's the moment off the moment diagram. And that's kind of a key relationship to understand, because what that has then is that relationship between the moment in the moment diagram and the stress that you're going to design the beam off of, see? Okay. So we can play some mathematical sort of games with that and rearrange this basic relationship here and end up with our basic design and analysis equation for a beam. And that tells us that the maximum normal stress is whatever the moment is off the moment diagram times c, which would be the maximum distance from the neutral axis to some edge of the beam, top or bottom, and then divided by the moment of inertia for the beam cross section. Okay? So that's the basic equation that we work with. All right. So we got any questions on that? All right. Okay, there you see a beam being loaded on a jig. You see where that stress starts to fail the beam. They just pushed on that thing till it failed, I imagined. You see that crack there starts to propagate from the bottom. That's a tensile failure there as they push down on the beam with that hydraulic press. Okay. And then it kind of works its way up through the beam. So let's have a look here. This is page 840. Let's have a look at analyzing this. Let's apply this MC over I thing. This is a very important equation that's used to design and analyze beams. So I'm sure you'll do something like this on the final, so you kind of want to get this figured out, you know. It's not something, I don't know quite how to, I never have the right words for this, but it's just a process. So you want to get the process figured out. The process is embedded in the equation. If you just look at the equation, which is in the upper right of the back side of your formula sheet, I don't number those equations anymore because I don't really need to, but it's in the upper right-hand corner of the back of the formula sheet. You got sigma is MC over I. So the process there to find the normal stress, which is sigma, is to find the moment off the moment diagram, find C off the centroid, and then find I that you calculate about the neutral axis, and then put them together. So, you know, the process is right in the equation. You got to find those three things and plug them in. That's how you find the stress. Okay? So what we have here is an L-shaped beam. If you're up in Taquina Hall, you can look up at the ceiling sometime. You'll see some L-shaped beams up there, big concrete beams. the bottom part of the L serves as kind of a ledge where they stack double T-beams to actually make the ceiling. That's a lot of the construction in this campus was done that way back in the late 60s, okay? So we have this L beam, and what we want to do is figure out what the normal stress is going to be. So this is the beam cross-section. What you're seeing up here is a sketch of what this would actually look like. Okay, so what I have is a combination of the cross-section of the beam, then I have a simple line drawing here for the load that's applied to it, 2,000 pounds pushing down. Okay, got a 10-foot span, and 2,000 pounds is 7 feet over from the support. So I went ahead and found the reactions. I show the calcs there for doing that. So we got a reaction of 600 on the left and 1,400 on the right. So why don't you go ahead and just take 2 minutes, fill in the shear diagram, and then from that generate that moment diagram. What we're really interested in here for doing this bending stress is that value there, because that's the maximum moment. So see if you can get that figured out. Just take a couple minutes at it, but you know, I've got the shapes of the diagrams in there, of course, so you just want to fill in the values. If you got any questions, you let me know. Ask your neighbor. Y'all getting to that all right? I'm good? Okay. So you got that reaction of 600, so you can go from 0 up to 600, then the 2,000 will push the 600 down to negative 1,400. Okay. Then you want to find the areas of the blocks, which give you the change in moment, which gets you, being as you're starting at 0, that'll get you the moment. Okay. That's kind of how that goes, right? So there we go. Something like that. We got any questions on that? And, and again, if you get competent at this, once you're competent at it, it's just so much faster doing the equations. Just bang, bang, you got it, Because real often when you're doing a full beam design, you're going to take the maximum value. That's really what you're after, is that number right there. Okay. All right, so we got any questions on that? How that was done? All right, now the other thing I did here at the bottom is, our beam length dimensions are often in feet. But we're going to do MC over I. C and I are going to be in inches, inches, C will be inches, I will be inches to the 4. So I want to get M into pound inches when I'm doing English units. So I just multiply by 12, and I get 50,400 pound inches. I'm just doing that so when I do MC over I, all the units match, and I'll get a pound per square inch stress. That's why I'm doing that, okay? Yeah, good. All right, so that's step the first there, is to find the maximum moment, because that's what I'll design the whole beam for. All right, now, and that's kind of, civil stuff, you're taking beams usually out of a catalog, and you're putting a building together. You're not going to custom design a beam for every application, Now, I would contrast that with building like a vehicle or an airplane or something like that. That's when you might, if I were putting this into something that I was going to mass produce, which buildings are not mass produced, but something I'm going to mass produce, I might custom design the cross section of that beam so it kind of peaks at 7 feet, because that's really where I need the strength of it. You with me there? So if I'm going to make 10,000 of these and I'm just going to kick these beams out, I might take the time to custom design a beam and make the shape fit that diagram that I'm getting into. But if you're doing a building, it's just not worth the design time and the fabrication time to do that. So if you do a building, which is a one-off, you design it once, and you're putting lots of time into the design work, you're probably just going to take that maximum value, pick a beam out of a catalog that'll work for that entire length at that maximum value, and put the thing in, and then get on to the next beam. So a little different approach. And I kind of see that as the civil world, where we design things once and build them, versus the mechanical world, where we design things once and build them 10,000 times as you're putting out a product. Okay, and you notice that on mechanical objects, often they've got kind of funny shapes on the structure sometimes, much more so than you see with civil, and that's one of the reasons why. Because you're manufacturing it, you're building it. The cost benefit of custom fabbing a beam for this, when you start building 10,000 of them, that's when it really starts to magnify and starts to get profit back, which is, remember, engineering is part of businesses. I mean, we build stuff safe. I mean, that's our number one priority. But number two is at a reasonable cost. Right? So I just want to point that out. And a good example of that would be like those truck trailers. Those flatbed trailers I was showing you a couple days ago. It's worth it to build them that way, because you build so many, and you'll get cost return on that for putting those wheel wells in there and kind of carving the beam out near the wheel well, because you don't really need that structure there. Okay, so just something to be aware of. Okay, but in the civil world, you just don't do that as much. Okay, centroid next. So why don't you find Y bar for that thing? Okay. So I'm just having you do this. I mean, really what I'm doing a little preview for the finals. You're going to have to do something like this. And there's just a series of steps. You have to execute the steps. So get this figured out. Okay, and of course I'll give you some homework and all that, but this is what you do. This is how you design a beam for bending stress, or analyze a beam for bending stress, I guess. Okay, so find the centroid. And we're just putting together all the pieces we've been working on for a week or so. That's what we're doing. About 4.33, something like that. We good? All right. So that's centroid. Now, we do this for two reasons. One is to figure out where the neutral axis is, because you calculate the moment of inertia about the neutral axis. So this is where the neutral axis is. And then the other thing is, this tells you what C is, okay? Because C is the distance from the neutral axis, which is right about there apparently, about 4.33, which, it looks about right. That's about where the centroid's at from what I could just looking at it. Looks, reasonable. Okay. And also we're going to find a moment of inertia about that. Right? So are we good with that? Okay, next thing there is I. All right, so what you do for I is you find BH cubed over 12. And then you find the area, you find the distance from the neutral axis to the centroid of the particular shape. So for that top one, the centroid's at 5, the neutral axis is at 4.33. Take the difference, it's 0.67. And then 20 times 0.67 squared. You add that to the BH cubed over 3. And you get the total for that shape. So the moment of inertia of A about the neutral axis is 175.6. Let's just see if we do the same thing for B. All right with that? Okay. So that's how that goes. Now, I'll point this out again, but that's a negative number, but it doesn't matter because that it goes inside the parentheses, you square it, so that those negatives always go away. So even if something is below the axis, it still will get you a positive moment of inertia. The only time you get a negative moment of inertia is if you're doing cutouts out of a shape, then it'd be negative. But other than that, the terms are not negative, regardless of where they're at, okay, where they're positioned. All right. Okay, so now, being as we got the neutral axis, we can find C, which is defined as the distance from the neutral axis to the edge of the beam. So that to the bottom, it's the 4.33. To the top, it's the total height of the beam, which is 10 minus 4.33. It's 5.67 to the top, okay? So we got one C to the bottom, another one to the top. And then to find the stress at the top, you just go the moment times the C value to the top, which is just the distance on the cross-section measured from the neutral axis to the top of the beam, divided by I. And it comes out to be 1291 pounds per inch squared. So that's the normal stress at the top of the beam. Okay? It's compression, because now the reason it's compression is how the beam's loaded, because the beam is loaded. It's just, it's simply supported beam. It's loaded, so the thing just bends like that, okay? So you got compression on the top. It's compression on the top, tension on the bottom, okay? So when you have positive moment, which you would have there, you get compression on the top, tension on the bottom. When you have negative moment, you get the reverse, okay? So once you got M, C, and I, you just combine them together and get the stress, MC over I. Okay. So we're going to the top, so we got compression up there. If we go to the bottom, the only number that changes is the C value, that's all. Okay, we good with all that? Good to go? So the stress at the bottom, 50,400 times 4.33 this time, because we're going to the bottom, times 221 or divided by 221.3, 986. Right. So that's basically how you do that. You just find M, you find C, you find I, and you plug them in. Okay. Now I went and found the allowable stresses for Douglas fir. So sigma compression is 1100, sigma tension is 1300. So could we make this beam out of Douglas fir? Would that be a good? Yeah, maybe not. The compression is looking a little risky, isn't it? So you might have to build a bigger beam, do something like that. The timber specs are really very, different timbers. It's hard to control the actual quality of it, of course, because it's cutting down trees. But there does seem to be a lot of safety factors built into that. But you just. The other thing is, I don't know if someone's mentioned it. I can't remember, but I was hearing a thing on the radio where they're starting to build. They're doing glue lam timber now. They're really getting into that, and they've built up. I think it's like 12-story buildings just out of timber structure. So that's getting to be something that they're working on, getting away from just concrete and steel for larger buildings, and actually learning how to make multi-story buildings out of timber. It's not just boards, they're cut and they're glue lammed together. It might be pressure treated too, so they're laminated and glued. Yeah, I guess you'd say that, yeah, right. Like the timbers, the fibers, the structure, and then that's glued and maybe even compressed too, I'm not sure. But they're working on that. They're doing a lot of research, and of course there's a lot of interest in that here in the Northwest because of the trees we grow and all that.
I think they're making the new forestry building.
Which,
The new forestry building?
Oh, I would be how surprised at that, yeah. So what, 3 or 4 stories maybe? I don't know what it's going to be, but yeah, something like that. Okay, yeah. So it's interesting, what else is going on. Okay. All right, so that's the basic way of analyzing that. So that's one of the things that you design beams for and analyze them for is bending stress. Okay. Now there's another thing too, and that's shear. So I guess the other thing I mentioned though is, you analyze just the edge because that's where the maximum C is, and that's where the stresses get maximized. So that's why we're analyzing that, because we're doing that by plugging in these values of C. Now you might say to yourself, well, why do I care if just the edge of the beam is failing, for that 1C value? And the reason is that failure propagates. Once things start to go, you're in trouble then. The whole beam will fail. So you see the initial failure on this one happened right there, but after that popped, well, now the whole beam cross-section is different now because you don't have the full cross-section for strength. And then now here's the bottom, and that couldn't hold it, and it just kind of works its way up. So, that's why we just analyze the edge, okay? That's the worst place, and that's where problems can start to happen, you might say. All right? So, we got any questions on that? Okay. All right. All right, so that's one of the main analyses that you do when you design a beam is the bending stress. There's another thing you look at too, and that's shear. So let's have a look at that. Now this is different than the simple shear we've been looking at here so far. So it's a little bit different. So it's something we want to be aware of. Okay. So what we're going to do, let's look at shear in beams, and I think this is 850. I'm always changing page numbers, so I'm not quite sure with this, but yeah, it's 850. All right, now this shear comes about when you load a beam over a given span. All right. So there's a picture of shear failure. You see that same jig there that's used. This is a standard jig that's used for testing these things. It's got 2 load points on it, okay? And that's done so you don't get kind of a stress concentration right where you apply the load. By using that head on it that has the 2 load points, you spread that out and get a more gradual curve. You're measuring these things you're interested in more directly then, okay? But what's happening here, you can see how that beam is flexing quite a bit, but you can see the shear failure right there, okay? So it's a different kind of shear. What's happening is those boards that have been glued together are sliding across each other so that you're getting a failure between the seams of those, okay? So notice what's happening, they're kind of sliding out. It's like the pages of a book when you bend it. Here all the pages are sliding one across the other, whereas on the other side they're not, right? Because the book is bound. But the shear we're talking about is a sliding failure between those planes. The key word there is slide. This thing slide, that's shear, okay? That's what a shear action is. Okay, so it's not like, when I think of shear, typically I think of like putting a nail or a bolt in a bolt cutter and just kind of going like that vertically and cutting it off. That isn't what we're talking about here. It's a different action. It's more based on the bending and the flexing and the sliding of one plane of atoms across the other. That's the type of shear failure we're talking about. So it's a different mode. So be aware of that. Okay? All right, so the shear stress, it varies along the depth of a beam. As you get into that more extreme bending, you get more shear is what happens. Or, I don't know, more pronounced bending, actually you get more normal stress, which actually ends up contributing to shear. What I just said earlier wasn't accurate. The shear actually maximizes in the middle of the beam for shear, but it's a function of bending stress is kind of how I think about it. So if we kind of pull out a little bit of dx here and look at that right there, what's going to happen is we're going to have those stresses that we were talking about earlier based on the bending, sigma times A, sigma dA, okay? And they're going to be forces that build up, pulling on this section of the beam. Now there'll be a slightly different moment, very likely, between the 2 sides of this little sliver of beam. So we're going to get slightly different forces, F1 and F2. So the difference in shear there will be F2 minus F1. Okay. Then if you divide it by this horizontal area, that'll get you the shear stress, tau. That's what we're looking at here. So again, this is a function of bending stress, is what it's a function of. Okay. Well, that's the basic idea of what the shear is we're looking at here. Okay. So we're looking at the sliding action of these different planes across each other. That's the type of shear we're considering. Now it's F2 minus F1 over that horizontal area. By the horizontal area, I mean that plane is oriented horizontally there like that. Now, for whatever reason, instead of F or P for shear force, we usually use V. So instead of being delta F over the horizontal area, it's delta V, and I don't know why, it's just what they commonly use to designate shear force. All right. So the forces, those different forces, F1 and F2, are caused by the normal stress. The normal stress is my over I. M is the moment, y is the distance from the neutral axis to the differential area there, and I is the moment of inertia. Okay, to find that's the shear stress, or excuse me, the normal force. To find these F1 and F2, you take that normal stress. I think I just misspoke. So normal stress is what we've got here. That's the my over I. We multiply that by the vertical area over which it acts, then we get the force. So F1 and F2 are found in that fashion. My over I times that area. Okay, so we're getting these forces like that. Okay. So to find the shear, we take the sum of those my over i's, which gets you the normal stress on a little differential area, and then multiply it by the dA, okay? So what we're looking at here is a little area like right down there. We're measuring from the neutral axis down to it. That's our y distance. We're getting m off the moment diagram. I is the moment of inertia of the entire beam. And then we multiply that by that little area that we're looking at. So the my over I is the normal stress. The area is the area over which it acts. Sum them together, or multiply them together, you get a force. Now the m is off the moment diagram, so that's not changing on the cross section. I is the moment of inertia of the whole beam. That doesn't change either, so the m over I can be pulled out of the integral, and you're left with the integral of y dA. A is that vertical area right there. Now that's one of the forces. We're interested in the change in force as you work your way from one to the other, right? We were looking at F2 minus F1 to get that net force on this area. So we call that delta of the force. Well, now we're going to call it delta V. And what's going to cause that delta is a slight change in moment as you move your way from one side to the other, okay? So there's delta V. The shear stress is that delta V, that change in force divided by the horizontal area. Okay, that's the area that resists these shears. It's this area here. Okay. So when we put all this stuff together, we're going to take delta V, which is m times the integral of y dAv divided by I, and then we're going to divide that by that horizontal area, which is delta x times the thickness of the beam. Okay. Then we put all that stuff together and we start to kind of work with it. Delta m over delta x is dm dx. That's actually getting us back to shear. Remember, when you do integration, you go from load to shear to moment. When you do the derivative, delta m dm dx, you get back to shear. Okay, so dm dx, which is delta m over delta x, is the shear, V. That's off the shear diagram. The I comes down there, the T comes down, and then you're left with this integral of y dA, which is called the first moment of area, otherwise known as Q. All right, that's the first moment of area there. So what you get down to then is the formula to find a shear stress. It's tau, the shear stress is the shear off the shear diagram, times this first moment of area, divided by I and divided by T. I is the moment of inertia for the entire beam. T is the thickness of the beam. Okay. So there's the shear formula. Again, that's another important one when we design and analyze beams. Okay. Now the maximum shear is different than the normal stress. The maximum shear occurs at the neutral axis of the beam because above the neutral axis you've got all one or the other. In this case I'm showing compression above the neutral axis. Below you have all tension. So what you end up with at the neutral axis is the biggest differential between the tension going one way and the compression going the other. And so that differential is maximized right at the neutral axis. So that's where tau is max. The minimum shear is 0. That occurs on the edges of the beam. So it's kind of different than normal stress. Okay? The maximum shear occurs in the middle of the beam. Okay. So there you can see where those failures are happening, kind of oriented in the middle of the beam. For some reason that seam there didn't go, but the other 3 of them did. Okay? So that's where that's maximized. Okay. Now, the general formula for shear is VQ over IT. There's also some maximum formulas that are derived. They're kind of empirically derived. Depends what kind of beam you've got. If you've got a rectangular beam, tau max is 3V over 2A. To me, what that means is V over A is what I would call the average shear. That's the normal way we were doing that for a long time, just finding V over A. In the beginning of the class. 3/2 I think of being like 1.5. So what you're doing empirically, they're saying the maximum shear is 1.5 times whatever the average is. Okay, that's kind of what that formula means to me, and that's for a rectangular beam. I don't know if that's super precise. I think that's kind of empirically derived. Okay, pretty good way of figuring it up. Same thing for a circular beam. It's 1.33 times tau average, okay, because V over A is tau average. Now for an I-beam, it's kind of funny. Again, they have this kind of rule of thumb way of doing it. You just look at the web because the shear is not very big in the flanges, so they don't play a very big role. So you take the web out and then you take the shear force, divide it by the thickness times the height of the web. So you're finding tau average for the web, and you're considering that to be the maximum shear stress. That's kind of done by experience, okay? Just for the web though. So you're ignoring the flanges when you do that analysis. Okay? So those are some formulas to find the maximum shears. The design values, I guess you'd say. So you got any questions on that? All right, let's look at another example here. Let's find the shear stress in a couple different ways here. Let's find the maximum shear stress, which would be what? Tau max that's a rectangular beam, so that would be 3/2 times the average shear stress. So let's go ahead and find that. And let's also find the shear stress at this particular location at point C, 80 millimeters up from the bottom of the beam. So what I mean by that is you come over to point C, which is a meter over. Then you go up into the middle of the beam. So we're in the middle of the beam there along that line that's 80 millimeters up above the bottom. That's what I mean by point C1. So why don't you get that shear diagram filled out? Because what we got to do, this is kind of similar to the normal stress concept here, we got 4 things now to figure out. Normal stress, you got to find moment, you got to find C, you got to find I. For a shear, you got to find the shear, the first moment of area, which is Q, I, and T. So why don't you figure out these things? Once you get that shear diagram filled in, figure out what the shear would be at point C1 and what the maximum shear would be, and find tau max. Okay. I'm going to go grab something here, so I'll be right back. Okay, so do that shear diagram drawn out and find the shear max and also the shear at point C, and find tau max for that thing too. All right, so I'm getting 9,000 on account of that reaction. Then when the load's applied, it'll drop 36,000 down to negative 27,000. So I'm getting VC is 9,000 because it's right in there. We got I there, 0.00045. The thickness of the beam is 0.2. And then if we need V max, we've got it right there. Even though it's negative, it's still a maximum. So I usually don't bother so much with signs on shears. It doesn't seem, so that'd be 27,000. Okay. So what we got there is we've got VQ, we got V, I, and T. I is just the moment of inertia of the cross section of the beam. The last thing to get there is Q. Now what Q is the area that would shear off times the distance from the neutral axis to the centroid of that area. And here it is. So hold on to this, we'll go over this maybe tomorrow at time, we'll see how that goes. Because we got a bunch of homework due Friday, you remember that, right? Yeah. So we'll go over that tomorrow. So let's just look at that real quick, and then we'll get out of here. But there we go. There's our beam. So what we do is we look if the beam were to fail at this point. We're looking at C1. That would be at point 1 is where it would fail. Remember, these fail horizontally, where one plane slips off the other. So we look at the area that would shear off if it failed at point C1. Okay, so that area would be the thickness of the beam, 0.2 meters. And then you'd multiply that by the height, the 80 millimeters. Okay, right there. So 0.2 times 0.08 is 0.016. That's the area that would shear off. Then you would take the distance from the neutral axis, which is in the middle of the beam, to the centroid of that area. Okay, and what that is we've got a 0.3 meter high beam, so that's 0.15, and the centroid for this thing, which is 0.08 meters high, is at 0.04. So the difference is 0.11. That's the distance from the neutral axis down to that centroid. So if we multiply the area times that distance, we get 0.0176, which is Q. Okay. So we can find Q, we can plug all that in now. So that I just, okay. So that if you're online, it might be worth screenshooting this screen here, just to have it. This does seem to be the most challenging part of calculating shear for people is figuring out Q. So we just plug all those numbers in, and that'll get us the shear at point C1. Okay, VQ over IT. All right. So that's we'll run through shear. Now we got those 5 problems due on Friday, and those are the shear and moment equation and diagram related problems. And then I'll give you some for Wednesday of next week, 361 and 362, and those are due on Wednesday. I also assigned one other one. Was it 344 or something like that? I can't remember. And what that is 361, right? No, I screwed up. It's 350. I'm sorry, 351 and 353. My bad. Here we go. Let's get that. 351 and 353. Here we go. That's what's due Wednesday. And Wednesday is the 11th. Okay. And it was also, was it 344? I think so. There's one I handed out. It's available on Moodle too. All right. So sorry about running a little late there.